My name is Jerry Barbarian, and I head up Arberg's additive business in the US. I've had the opportunity to spend over a decade in the additive industry. When I started in additive, I remember having to convince people that parts were not machined, they were grown. I gather many of you remember those days. It's been amazing watching 3D printing expand from an unknown technology to a widely adopted solution for prototyping to production and everything in between. Arberg's additive technology is exciting because it brings something new to the market, the ability to use production materials, taking additive a large step closer to true production parts.
My name is Michael Salinas, and I support Arberg's additive business in Germany and Eastern Europe. After joining Arberg in 2014, I spent 4 years in our R&D department working on qualification and development of materials. Together with my colleague Jerry, we will give you a comprehensive insight into Arberg's plastic freeforming technology, which will also cover the range of materials that can be processed. Before we discuss the technology, Jerry is going to share a short story with you.
Thank you, Michael. I would like to share a brief story regarding one of our customers, BRAUN, a very well-known medical company that currently has 2 freeformer systems. The company utilizes 3D printing to create custom, patient-specific drill guides for knee surgery. You can see the surgical guide on the left, and on the right, a picture of the surgery using the guide. I tried to pick a less graphic one for the majority of us that don't want to look directly at that. The patient-specific surgical guides used to be created with a powder-based 3D printing technology, but the company was concerned that no matter how well they clean the parts and sterilize them, there was still a risk of some powder left over from the build process somewhere on the part. With a risk of possible contamination, they started looking at other options. They are now looking to the FREEFORMER and Sabix Ultim 1004 as a solution. This grade of Ultim is biocompatible and sterilizable. The FREEFORMER is an ideal solution because it can process the natural material and there's no worry of any leftover material that could possibly cause contamination. This story is like so many others we hear from our customers praising the FREEFORMER. So let's take a look at additive and the technology. I'm sure most of you are familiar with additive, also known as 3D printing. It's probably why you're attending this virtual event. I bet that most of you are dealing with today's ever-tightening product development timelines too. With more product variations, shorter product life cycles, and the tightening of budgets, there seems to be one common conclusion. We're all being asked to do more in less time. There are many variations of 3D printing that can help your organization with fit and form checks through your design cycle. We can quickly try several different iterations and perfect our design's look and feel. However, many companies I speak with tell me they are left wanting when it comes to functional testing. Today's technologies can't make a model that accurately represents their final design, whether it's the multiple components needed, the parts density, or the material itself. Nothing we know of is getting the job done for true functional testing. That brings us to the best unintentionally kept secret in additive, the Arberg FREEFORMER.
The Arberg plastic freeforming, which is the processing technique we apply in the FREEFORMER, is an extrusion-based additive manufacturing technology that makes it possible to process qualified molding-grade pellets. In the material preparation unit, the pellets are plasticized by a rotating screw in a heated barrel. The plastic melt is then pushed towards the nozzle and discharged as a string of droplets by opening and closing the nozzle. The melt pressure which is necessary to discharge droplets is generated by the forward movement of the plasticizing screw. A precise and reproducible discharge of droplets is enabled by a non-return valve that closes as the screw advances in the barrel. The nozzle is closed by expansion of a piezo actuator located in the top area of the discharge unit. When the nozzle is opened by the mass pressure, the material flows through a 10-micron gate at the tip of the nozzle. I mentioned the size of the gate because particles need to be smaller than 10 microns to flow through. the droplet discharge is synchronized with the movement of the tray, resulting in discharge frequencies of up to 300 droplets per second. Typical layer thicknesses that can be realized are in the range between 100 to 300 micron. Individual optimization of the part quality requires the consideration of several factors, for instance, the design of the part. For additive manufacturing, the absolute part precision is mainly limited by the layer thickness. Consequently, the minimum wall thickness of the part will be one important design criterion. For the plastic free-forming process, we recommend a minimum wall thickness of 600 micron. With any open system comes the need to qualify materials. Compared to other additive manufacturing technologies, the variety of thermoplastic materials that can be processed is considerably higher. As long as free-flowing pellets are used, the material can be either hard or soft, ductile or brittle. There are virtually no restrictions when it comes to material properties. Processing temperatures and dosage settings for the plastic free-forming process are very similar to the settings used for injection molding. The most intriguing feature of the plastic free-forming technology is the nozzle closure system, which makes this process unique in the additive world. The ability to control the discharge of small droplets makes it possible to handle thermoplastic materials with different rheological properties. The process even works for materials with very low viscosities as long as the melt pressure is high enough to open the nozzle. In order to obtain the best part quality possible, we need to take into account that different material properties will lead to a varying size and shape of the droplet. The freeform data processing software allows the user to adapt these parameters for every new material to be qualified. The same applies for the ability to vary the density of a part. Notice that the density can be affected by spacing out the droplets. This enables the user to adjust the mechanical properties according to the requirements, even within a single part. The packing density of the droplets can reach very high levels. Here you see a printed polycarbonate cube. This piece was polished on both sides to show not just the clarity, but specifically the density of the part. Notice no air bubbles are visible. To further prove the point, a CT scan was done on the part. In the image on the right, you can see the achieved density is impressive. The unique combination of processing pellets and droplet discharge with the nozzle closure system allows for covering a wide range of material properties. Amorphous thermoplastics such as polycarbonates or amorphous polyamides are widely used materials in extrusion-based additive technologies because of their low shrinkage. Not commonly seen in additive are semi-crystalline materials such as polypropylene. However, we have been successful in qualifying several customary polypropylene grades for the freeformer. The unique properties of this material open up the possibility to realize parts with snap fits and living hinges. We also had success in printing different thermoplastic elastomers such as TPU, TPV, or SEBS with a range of Shore A hardnesses from 30 to 95. A very interesting class of materials are biodegradable polymers such as polycaprolactones that are used for controlled drug release applications and long-term implants. Those materials are well suited for the free-forming process so that printing patient-specific implants is a very promising application, as some of our customers have already shown. Special materials successfully processed with the freeformer include compounds with conductive and flame-retardant additives. Parts with complex shapes require support structures during the printing process. Water-soluble or alkaline-soluble materials are the preferred solution for this purpose, because of their ease of use together with a harmless solvent. We offer different support materials that are compatible with most of the materials we have qualified so far. On the next slides, Jerry is going to talk in more detail about some selected materials and their applications.
For this next section, I'm going to share my video. I'd like to show you some example parts. The FREEFORMER is capable of printing multiple materials in a single build. You can see here some examples of two-component parts. As an open system, it's up to the user to decide what combination of materials are used. As long as the materials play well together, they can be printed together. Another possible option is to have multiple materials loaded, not for the same build, but to quickly switch between different materials and avoid material swaps. For some geometries, such as this simple gear, support material may not be necessary. Notice there's no undercuts or internal geometry here. If support material is not necessary, we can load up to 3 individual model materials in order to print them all at the same time or back to back without changing materials out. In other cases where support material may be necessary, users can choose to print 2 materials. Normally, users would add in a rigid and a flexible. Here's an example of a rigid and a flexible material printed in the same part. You can see the black section is rigid, and the red section is a flexible gasket. Printing soft materials is certainly an area where the FREEFORMER excels. Whether it's soft materials for medical applications, here's a flexible Shore 30A medical grade material. And notice how we've used the ability that the FREEFORMER has to change the density in the middle of the part, but leave the density full on the outside. And that creates a durable but filter-like appearance and flexibility. What about materials for automotive? Here we have a flexible corner door jamb or weather stripping for a car door. You can see the complexity here. Or any other flexible parts. This is a great example. You can see how thin this is and how durable it is. And this is my favorite example, a simple bellow. However, because it's made of real materials, you can do this. No breaking, no tearing, no ripping. Real materials. When it comes to rigid materials, we have optimized material profiles for a variety of rigid materials. Some standards like ABS or PCABS, some more specific ones like V0 flame retardant materials, and some semi-crystalline materials like polypropylene. Here's a few examples. This is a PCABS part. You can get a good idea of the surface finish on this part. Here's a polypropylene flip-top cap. You can see here the living hinge. I've had this for about 11 months now and have been playing with it, and still the hinge works wonderfully and there's no ripping. Also snap fit parts with polypropylene. Works great. We also have some specialty materials. So with an open system, if you can think it, you can do it. So a really cool example of a specialty material is this flexible piece of TPU. You can see here that there's 2 different colors, clear and black. The clear is just regular TPU. The black has carbon nanotubes embedded in it, which creates a conductive material. And here you can see we've got an LED light embedded in there. So if I take my battery and I plug this guy in, you can see that the LED light is now on. A great example of conductive material. Just one of the things you can do with the FREEFORMER. With the FREEFORMER, we can use medically approved materials to create medical parts, or take it a step further and use highly specialized medical materials such as Resomer from our partner Evonik. Resomer is a bioabsorbable material that can be used for a variety of applications, such as implants or fracture plates. They even make a version that contains a ceramic additive, and that additive can help promote bone healing. That material can be used as a fracture plate or as a scaffold. We've spoken a lot about medical applications with the FREEFORMER. So let's round it out by saying that the FREEFORMER is a system that you could put directly into the clean room. It has ISO 6 production possibility, innovative temperature management, closed air circulation, and the entire build environment is done in stainless steel. We have several partners that are currently using the system in clean rooms, and if you have any questions about that, we'd be happy to walk you through it. Since we're using the same material, we're often asked how strong printed parts are compared to injection molded parts. We did a study with some injection molded dog bones and printed dog bones to see how close they really are. The black bar is a molded dog bone. The dark green one is printed flat to show the strength in the X and Y direction. And the lighter green one is printed standing straight on its end to show the strength in the Z direction, generally viewed as the weakest direction as a result of the material layering process. Now you can imagine the results can vary depending on the material printed. However, this is a great example of how close in material properties the printed part on the FREEFORMER can get to a real molded part. I would like to take the next few minutes to show you a real example of the FREEFORMER's abilities for low volume production. Here you can see a spacer for a connector on Arberg's injection molding machines. Now, the connector is only used once in a machine, and it only pertains to certain models. So as a result, Arberg only calls for approximately 1,200 of these parts a year. So if we analyze the volume breakpoint for the FREEFORMER versus injection molding this part, we have to think about the setup cost for molding versus the per part cost for the FREEFORMER. To calculate what was a better direction, using an injection molding system or using the FREEFORMER to produce this part, we decided to look at injection molding first. To mold the part, we can use the Arberg all-rounder molding system with a 4-cavity mold that can shoot 4 parts in 8 seconds. It's approximately an €8,000 setup or $9,500. And then the cost per part is extremely low. So we'll just concentrate on the setup costs to help drive our calculation. When looking at the FREEFORMER, we can build about 70 parts per build tray in our smaller 200-3X system. It's approximately 3 minutes per part, and the part cost is €149 or $1.77 US. So this is where our calculation ends up. If we look at the yellow line, that's the calculation based on injection molding. We started our setup cost of €8,000 and notice that the line only slightly increases as we increase the amount of parts we produce. If we look at the line in green, that's our FREEFORMER. Now the FREEFORMER has a steady 45-degree angle because for every part we create, it costs €149. However, if we look at where those two lines intersect, that's way up at over 5,500 parts. So since we don't need that many parts, we only need 1,200 parts, we can see that it makes much more sense to create these parts on the FREEFORMER. It'll cost far less, and we can choose when we want to create the parts, thereby not adding extra inventory when it's not needed. And finally, the FREEFORMER systems. On the left-hand side is our 200 model. This is our 2-nozzle unit. A standard setup for this unit would be 1 model material and 1 support material. On the right-hand side is our larger 300 unit. This unit has a larger build tray, the high temp printing ability, and 3 nozzles, commonly set up with 1 support material and 2 model materials. I say commonly set up because, as we've discussed so far, with an open system, the machine will do whatever you, the user, ask it to do. Thank you for joining us today. To wrap up, the FREEFORMER sits in a class of its own, a flexible and open platform utilizing thermoplastic pellets. It can create single or multi-component parts in rigid or flexible materials at a very low cost per part. Part strength is near that of injection molded parts, and the user has the ability to customize the density of their parts. That brings us to the end of our presentation. We hope you enjoyed it and will come visit us at our exhibit booth to discuss your applications and how the technology could impact your business. Thank you.